All right, so here is the Picard-Lindelöf theorem again, and I have simplified it a little bit. Right, so here I'm assuming that f of ty is continuously differentiable on a certain rectangle in a neighborhood of the initial point t0, y0. Well, the actual condition in the theorem is a bit more complicated, but again, if a function is continuously differentiable, then it also satisfies those two conditions. It is going to be continuous in t and is going to satisfy the Lipschitz condition in y. Well, however, verifying that a function satisfies the Lipschitz condition directly is hardly possible, while verifying that a function is continuously differentiable is easy. So usually we know that it satisfies the Lipschitz condition from the fact that it is continuously differentiable. Okay. Now, further intuition about this. This theorem tells us that if we have some process in nature that is governed by a differential equation, then we can always solve the model and compute that there is no kind of randomness there. So we can always compute it for any with any given precision for any specific time. So I'm going to give you an example of this. So my example is about growth of cancer tumors. Right? So if you have a cancer tumor, then what they do in life sciences, I'm not an expert in life sciences, I don't know exactly how it works, but what I've read about is that the process of cancer tumor growth is governed by the differential equation dy dt. If y of t is the mass of the tumor or the size of the tumor, of the cancerous tumor, then it is something like the logistic differential equation. So it has two parameters, the intrinsic growth rate and the carrying capacity, but it's a bit different. So it's r times y times logarithm of k over y, where r and k are parameters. And so it means the following. It means that, for example, if we know that the values of the parameters for some specific tumor, let's say if we know that dy dt equals 0.01y times ln of 0.045 over y, and we know that initially the size of the tumor, I don't know how they are exactly how they're measured, but let me just write some numbers here just to be specific. Right, so it means that if we have a differential equation and we know that in the neighborhood of the initial point, so the initial point in t is 0, and here the right hand side just does not have t, so of course it is continuously differentiable. Its partial derivative with respect to t is just 0. So with respect to y, it is the product. Well, in order for the right hand side to be defined, y cannot be 0 because there is division by 0, but as long as the initial value of y is not 0, it is continuously differentiable with respect to y, so it satisfies the Lipschitz condition too. So it means that if we know this, then we can calculate, at least theoretically. Maybe we cannot solve the differential equation explicitly in the sense that we cannot find the formula, the explicit form that satisfies this differential equation. But due to the fact that we have the existence and uniqueness of solutions, it means that at least numerically we can compute y of t for any given value of t with any given precision. So for example, if this is the growth of tumor and t time is measured in days, it means that at least theoretically we can compute y of after 10 days, and we are going to see how big the tumor is after 10 days. And then we can say, I don't know, change the differential equation so it includes the therapy, or it does not include the therapy. We can make predictions for the life of the patient based on that information. And this is thanks to the fact that we have the existence and uniqueness theorem. Because of existence and uniqueness theorem, we can at least numerically compute the solution, but it is unique. So it means that these two conditions, they completely determine the evolution of the tumor. That there is no randomness here.